So today I'll be discussing binary phase diagrams, and I figured what better way than to start with a real world application, salting roads, especially since we are in the season of winter. So highway workers actually use salt in two ways, to melt ice that is already on the roadway and to prevent ice from forming on the roadway. So let's say, for instance, a snowstorm is actually forecasted to be coming your way. Oh no, there's a storm! Okay, and here's you, and you're walking in the snow, and then you see someone pouring salt all over the road, and you're kind of like, why are they doing that? So as the storm hits, snow starts to fall, and the road surface is warmer than the air, so the first flakes melt. And why is it that they melt? Well, I'll show you. In 5, 4, 3, 2, and 1. Then you see a big truck throwing snow over some wintry road, and like everything else in the picture, you can bet the salt's pretty cold. So this begs the question, how could it be that something that isn't hot is melting the ice? Turns out that salt isn't actually about melting, it's all about freezing. So the freezing point of pure water at rest is actually 32 degrees Fahrenheit and 2 degrees Celsius. When the temperature of water reaches a freezing point, it's normally free-flowing molecules get trapped into organized crystal structures. This is how ice is formed. Salt disrupts this process, and upon hitting water, salt breaks up into 2 ions. 1 sodium and 1 chloride. These 2 ions move around and take up space in between water molecules, pushing them apart and frustrating their potential links to form ice. This disruption is called freezing point depression. Basically, salt lowers the freezing point of water, but there is a limit. How can that be? I'll show you with something called the binary phase diagram. In a little bit. In 5, 4, 3, 2, and 1. So here's the phase diagram for sodium chloride that I was just describing. So here we have our salt solution. We have the freezing point. We have our ice plus our salt solution, the eutectic temperature of salt, and our solid salts and ice. And then we have our axes. But this is very nice and colorful, but for I thought I would simplify this diagram. So here is a simplified version of it. So basically all the action that's going to take place is on the left-hand side of the diagram, and that's why there's like a lot of the horizontal scale is missing, represented by the broken zigzag here in the scale. Yeah, so these areas actually show what you would see if you had a particular mixture of salt and water at a given temperature. For example, if the temperature was below negative 21.1 degrees Celsius, for instance, you would always see a mixture of solid salt and ice as seen here. So there would never be any liquid or whatever proportions of salt and water you had, and at temperatures above this, what you would see would depend on where your particular set of conditions fell in the diagram. You just need to notice what area the conditions fall into. For instance, in here they fall into the salt solution, right? And I even put it here. If you had a mixture of this composition at this temperature, you would just have simple salt solution. So what do these lines mean? So here, the green line represents the effect of increasing amounts of salt on the freezing point of water. Up to the point where there is 23.3% of salt in the mixture, the more salt, the lower the freezing point of the water. You see that here as well, it's going downward. So the second line is actually a solubility curve, this one, and for salt in water. In the case of a salt solution with concentrations of salt greater than 23.3%, the solubility curve shows the temperature at which crystals of salt will appear when you cool a solution of a given concentration. And our final line is, this line is simply drawn across at the lowest temperature at which a mixture of salt and water can contain any liquid. This is actually known as the eutectic temperature. The particular mixture of salt and water containing 23.3% salt, which freezes at this temperature, is known as the eutectic mixture. Here it is, right here. And basically, the phase diagram is used to find out what happens if you cool salt solutions of a particular concentration. Like at eutectic point, in this diagram, at the eutectic point, actually you'll start to get both ice crystals and salt crystals forming. If you keep cooling it, you will obviously end up with a solid mixture of ice and salt, but you are basically moving straight from the salt solution area over here of the phase diagram into the solid salt plus ice area. And I put it here as well, that basically here you cool solution with this composition here, and basically this leads to here the eutectic point, crystals of ice and salt both start to form at that eutectic temperature here. And the next diagram, basically to find out what is actually in the mixture, you draw a horizontal tie line through the point showing the temperature you have got to, and you look at what it hits at either end. For instance, in this case, on the left, it hits the vertical axis showing 100% water, and that's pure ice crystals though. And on the other end, it hits the sloping line, or this one, and this tells you basically the composition of the remaining salt solution. And as the mixture continues to cool, it will eventually reach the eutectic temperature. At this point, all the rest of the solution will turn to a solid, a mixture of ice and salt crystals in this here region. Yeah. And furthermore, yeah. So actually, so let me show you some liquid solid phase diagrams that you're probably more familiar with from class. Here's one in which we have 100% of composition A and 100% of compound B, compound A and compound B. And here's composition, and here's our temperature. Let's go. Okay, and here we have our melting point pure A and a melting point of pure B. And our eutectic point is temperature at which a particular eutectic mixture freezes or melts. Here's our eutectic point. Okay. So the line above which the entire sample is liquid is termed as the liquidus line. And here's our eutectic point again. And here we drew in our alpha, which represents solid compound A, and our beta represents solid compound B. And here we drew in alpha plus liquid and beta plus liquid, and here we have this pure solid below the eutectic line. Okay, and furthermore, actually this is a really good example from the book that I want to discuss. And basically, if you consider the molten liquid of composition A1, when the liquid is cooled here, starting A1 here, right, and you cool it to A2, the system enters a two-phase region labeled liquid plus A. So almost pure solid A begins to come out of solution, and the remaining liquid becomes richer in B. So basically on cooling to, where is it? A3 here, more of the solid forms, and the relative amounts of solid and liquid, which are in equilibrium, are given by the lever rule. At this stage, there are nearly equal amounts of each. So the liquid phase is richer in B than before its composition is given by B3, right here, and because A has been deposited. And at A4, there's actually less liquid here than at A3, and its composition is given by E. This liquid now freezes to give a two-phase system, almost pure A and almost pure B, and cooling down to A5 actually leads to no further change in composition here. Also, I want to mention that the vertical line through E, right here, corresponds to the eutectic composition, and basically a solid with the eutectic composition melts without change of composition at the lowest temperature of any mixture. So another one important phase diagram are liquid-liquid phase diagrams. So let's just point out what we have here. We have our T prime, we have our A prime, you have an I prime, an I double prime, and A double prime. Okay, and here's our temperature. We have our two phases and our one phase, and our mole fraction xn. So some background and some real-world application actually are that, well anyway, partially miscible liquids are liquids that do not mix together in all proportions. An example, a real-world application is hexane nitrobenzene, that when the two liquids are taken together, the liquid consists of two liquid phases. One is saturated solution of hexane in nitrobenzene, and the other is saturated solution of nitrobenzene in hexane. So because the two solubilities vary with temperature, the compositions and proportions of the two phases change as the temperature is changed. And we can use this here, temperature composition diagram, to display the composition of the system at each temperature. So suppose we add a small amount of nitrobenzene to hexane at a temperature T prime. Nitrobenzene dissolves completely. However, as more nitrobenzene is added, a stage comes when no more dissolves. The sample now consists of two phases in equilibrium with each other. The more abundant one consisting of hexane saturated with nitrobenzene, the less abundant one a trace of nitrobenzene saturated with hexane. In the temperature composition diagram, the composition of the former is represented by the point A prime here, and that of the latter is represented by the point A double prime. The relative abundances of the two phases are given by the lever rule. And basically, when more nitrobenzene is added to the two-phase mixture at the temperature T prime, here hexane dissolves in it slightly, and the overall composition moves to the right in the phase diagram. The compositions of the two phases in equilibrium remain A prime, E prime here, and A double prime. The difference is that the amount of the second phase increases at the expense of the first, and a stage is reached when so much nitrobenzene is present that it can dissolve all the hexane, and the system reverts to a single phase right here. Basically, the point representing the overall composition and temperature lies to the right of the phase boundary in the illustration, and the system is a single phase at this point. So that's one liquid-liquid phase diagram, and the next one is actually another real-world application is fractional distillation. So fractional distillation is a process used to separate a mixture of liquids that have different boiling points. When the mixture is heated, liquids with a low boiling point evaporate and turn to vapor. Liquids with a higher boiling point remain as liquid, and the vapor can then be separated from the liquid. Fractional distillation is used to separate crude oil into fractions with different boiling points. So why is this important? Why am I telling you this? Well, because the process of fractional distillation can be represented by a series of steps on this temperature composition diagram here. So the initial liquid mixture may be at a temperature and have a composition like that represented by point A1, for instance, here. And it boils at the temperature T2, and the vapor in equilibrium with the boiling liquid has composition A2 prime. Right here. If that vapor is condensed to A3 or below, the resulting condensate boils at T3, this is T3 here, and gives rise to vapor composition represented by A3 prime. As the succession of vaporizations basically and condensations is continued, the composition of the distillate moves towards pure A, the more volatile component, and the pure A would be here, A4 in that case. So yeah. And basically, don't forget that we saw binary phase diagrams in lab at the beginning of the semester with the naphthalene and diphenylamine experiment for your own reference. Well, thank you very much.